Okay guys, in this problem we want to calculate the acceleration of the system because the three masses are attached to each other, so they supposed to have the same acceleration, and the tension in the stream between M1 and M2. I know that the problem says that M0, M1 and M2 are equal, but when I looked at the solution in the back, they treated like different numbers, M0, M1 and M2, so I'm going to solve it like that. As you see, Irodov used W for the acceleration, I don't know why, and K for the coefficient of friction. Instead, I'm going to use mu and A. Now pause the video and try to solve it. So this is the problem in the text. They call W for acceleration, I don't know why, and they want the tension between object 1 and 2. So between 0, this is going to be T0, but that is not being asked, and this is T1. That's what is being asked. The tension between mass 1 and mass 2. Okay, what is given is the coefficient of friction. They call it K, so we'll call it mu, and the three masses. They claim that the masses are equal, but when I look at the solution in the back, they solve the problem like with the three symbols. They didn't find the solution like they have equal masses. So I will do it with the three masses, so just the same way as earlier. So this is going to be my direction of motion. This is what I will call positive, because you know the system cannot go back, cannot go in the positive direction. And this is my one-dimension problem. This is one-dimension problem. If you do it x and y, you know that the acceleration in this y-axis is equal to acceleration in that y-axis. So if you wonder why the accelerations are equal, it's because, for example, the length, because there is a constraint equation. Yes, everybody says A1, A0 equals A1 equals A2 because the string, the thread does not stretch. And that is, but if you want to prove it, you know that's what happened. But if you want to prove it, for example, you have to say this length over here, L1, is, let's say, position 1 minus position 2. And this length, this piece over here, does not stretch. So you could take derivative on this equation. The derivative of a constant is 0. And you do two derivatives, right? First derivative and second derivative. You get the first derivative is the velocities are equal, obviously. And you do the second derivative and you get A1 minus A2, or A1 equals A2. And the same thing you do over here. This length does not stretch. So this y position, you find the equation for the length and you do the same thing. So everybody say it. The three accelerations are the same. But why? Because this is there are two constraints equations, that this piece of thread is constant and that piece of thread is constant. And if you take derivatives of the constraint equation, then you get that A1 equals A2. I know it's common sense, but in this problem, this doesn't help. But in more advanced problem, it's very important to find the constraint equation of your system. In this case, there is two constraints equation, one with this length and one with that length. So once you have that, and you think that this is one-dimensional problem, but you're going to have three equations because you have three objects. So the first equation is for object 1, and for object 1 you have T0 and M0G. So you have M0G positive because it's down, T0 negative because it's up. Just be consistent with this highlighted direction, and M0A. Again, A1 equals A2 equals A3 equals A0 equals A1 equals A2 equals A. So I don't need to put A0, A0 over here. The second object, you have T0 and T1. Friction, I will put it under friction 1, which is mu M1G. So positive is T0, then negative is T1, and negative is mu M1G equals M1A. And the third object is T1 and F friction 2. Friction 2 is mu M2G. Okay, remember that friction is mu times the normal force, and the normal force is equals mg for objects 1 and 2. So I'm keeping the steps that this object is not sinking in the table and this object is not sinking in the table. So m2g equals to normal force, m1g equals to normal force. So that's the third equation. Positive T1 minus mu M2G equals M2A. Now, as you can see, this is negative T0 and positive T0. So I'm going to add 1 and 2. 1 plus 2. So is M0G. The T0s cancel. So I got minus T1 minus mu M1G. And now A is a common factor. A. Okay. Now, if you see, this equation has what is being asked, the acceleration and T1. That's the reason I add these two. I could add 2 and 3 to cancel T1, but they are not asking T0. For that reason, I didn't add 2 and 3. I don't need to. Why? Because now I have the third equation. Let's call this 4. The third equation is plus T1 minus mu M2G equals M2A. So now I'm going to add 4 and 3. As you see, the T1 cancels, and I have M0G minus mu M1G minus mu M2G. And now I take A as a common factor, and I got M0, M1 plus M2. This is the equation for A. I just find the equation for A. I will take G as a common factor because A has units of G. So here I have M0 minus, and I will take mu as a common factor in these two. And this is the equation for the acceleration. It has units of G, and then m0 minus the coefficient of friction and the sum of the masses. Okay, I check the solution and this looks correct. And why this equation is important, because you know that the motion can only be in this direction. The motion can only happens in this direction, assuming that the initial conditions are zero velocity for each object. So how come the acceleration is always positive if mu mass 1 plus mass 2 has to be less than m0? And this is the condition for motion, and you could do an experiment to prove it, to see it experimentally. Suppose that you calculate the coefficient of friction. You calculate the coefficient of friction, and if it's less than this number, which makes sense, this is m0 is what is being pulled by gravity. If this condition holds, then the object accelerates downward. You could do that experiment, change the masses, and see that motion only happens if this is true. Now let's go to find the tension. I could use equation 3 to find T1, because so this is equation 3. And times the acceleration, so I will place the acceleration over here. So over here is the acceleration, g m0 minus mu, the sum of the table objects and the sum of all the objects, m0, m1, and m2. Okay, so move this to the other side. Times the bracket. Now we'll take, because it has to be units of force, I will take m2g as a common factor. And now I have over here mu plus that fraction over there. And now I will put this similar to the solution that is in the back of the book. So it's mu m0 m1 m2 plus m0 minus mu m1 plus m2. Okay, so mu m1 cancels with mu minus mu m1. So this and this cancel. You need to multiply, but I'm doing it on my head. Mu m2 cancel with minus mu m2, so this cancel too. So the only thing left is mu. Oh no, I can't. This is the one that cancel. M0 does not cancel. This one and this one. So I got mu m0 plus m0, this one and this one, divided by the sum of the masses. Take m0 common factor, take m0 common factor, and you get m2g m0 1 plus mu m2. and this is the tension between between 1 and 2. And I have the solutions over here in the book. I don't know, it doesn't show one, but I checked it and they are right. And it's important to notice that I put the signs of the forces over here. Okay, so the tension must always be a positive number. You see, this is a positive number because I put the sign, the direction over here. So this is T1 is the magnitude of the force, and it's always going to be like that in this program. Again, this is the acceleration and this is the tension, and this is the condition for motion to happen. That is, mu has to be less than this. If that holds, then the system accelerates downwards. Now we show you a shortcut. If you think that this is a system and you want to find the acceleration of a system, this system has mass m0, m1, and m2, and it's moving with acceleration a. It's not three objects, it's just one object. And now here on the left, you have to put all the forces that are acting on this system. Some are positive, some are negative. For example, m0g is positive. If this, remember, this is my positive direction. So m0g is positive. Then you have minus t naught, positive t naught. They cancel out, as you can see. Then you have negative t1, negative mu m1g, and last you have positive t1, negative mu m2g. And this cancel, and it's very easy to find the acceleration this way because, as you can see, it's m0g. I take mu common factor, mu g common factor, and m1 plus m2. And you take g common factor and you get exactly the same equation, but much easier. Think it that you have forces acting in one direction and forces acting in the other direction, but if you add them all together, you get the equation for the acceleration right away. Did you get the equation for the tension right away? Now you could just put the equation for M2, and the reason you use the M2 is because M2 only have two forces acting on it, so you just put positive T1 minus the friction that is in this direction. Thus, friction 2 equals M2A. So for T1, and this is the same thing, you just substitute that over there. So this is a shortcut. Think this is a system of three forces, and some forces are acting in downward to the left, and downward, and some to the right. Downward is positive, upward is negative, left is positive, rightward is negative. As you can see, the tensions, you can see that, you can also see it. What are the internal forces of the system? The internal forces are the tensions, and look, they cancel out. And what are the external forces on the system? Is gravity and friction. Gravity and friction. And in that way, it makes sense. It makes sense just to use one equation to find the acceleration, and then use the easiest one to find T1, that is the object on the far right. Why you are not using the object on the left or M1? Because M1 has three forces acting on it, and one of them is T0, and you don't know what T0 is. So this is the shortcut on how to do this problem.